Right, question 15. Now I've already written down that we know this. The mass of the cesium-137 that we got is 1 microgram, and the half-life is 28 years. So what's the initial activity? So we're going to do that using this equation. A equals minus lambda n, and in fact we can just ignore the minus. So the first thing to do is work out the decay constant, which is ln2 over 28 years. Now I want to get this into per second rather than per year. So I've got to convert my years into seconds. So 365 times 24 times 60 times 60. Okay. And that's going to give me an answer of 7.85 times 10 to the minus 10 per second. Okay, so there's my decay constant. That's the first thing. Now the next thing is this. The number of atoms that we've got in this sample is equal to the mass of the substance, or mass of the sample, whatever you want to call it, divided by the mass of one atom. So the mass of substance here is 1 times 10 to the minus 6 grams, but if you want to get that into kilograms, it's 1 times 10 to the minus 9. So let's perhaps do that here. Okay, the mass of the substance is 1 times 10 to the minus 9 kilograms divided by the mass of one atom. Now we've said this before in a previous question. This 137 here tells us the mass of a cesium atom is equal to 137 unified atomic mass units. Okay, so we've got the mass of one atom is 137 unified atomic mass units, but we want to convert that into kilograms. And remember, 1 U is equal to 1.66 times 10 to the minus 27 kilograms. We need to have this in kilograms and this in kilograms. So we're going to multiply that by 1.66 times 10 to the minus 27. Okay, so let's do that calculation. 1 times 10 to the minus 9 again messing up here, divided by 137 multiplied by 1.66 times 10 to the minus 27. That's going to give us 4.40 times 10 to the 15. Okay, so 4.40 times 10 to the 15. Now, that gives us the number of atoms present in this mass of cesium. So we can now work out its original activity or initial activity just by doing A equals lambda n. Now lambda was this, 7.85 times 10 to the minus 10. The number of atoms is 4.40 times 10 to the 15. So that's going to give us 3.45 times 10 to the 6 becquerels. Okay, 3.45 times 10 to the 6 becquerels. That's part A done. Now part B is pretty straightforward. What's the activity after 100 years? Well, we're going to use the equation A equals A naught e to the minus lambda t. We've already got lambda here. We've already got A naught here, so we just put the numbers in. So A equals, so this is actually A naught, okay? I should have put that on here. This is the original activity, isn't it? So it's actually A naught. Okay, so 3.45 times 10 to the 6 multiplied by E to the power of minus 7.85 times 10 to the minus 10 multiplied by the time. Now the time is 100 years, but we've got to convert that into seconds. So we're going to multiply that again by 365 times 24 times 60 times 60. Okay, and that should give us our answer. So it's 3.45 times 10 to the 6 multiplied by e to the power of minus 7.85 times 10 to the minus 10 multiplied by 100 times 24 times 60 times 60 times 365, which gives you, whoops, I've done something wrong here. What have I done wrong? I haven't put the bracket on there. Okay, There we go. We're going to get 290195 becquerels, okay? Part C asked us for the disintegration constant, also known as the decay constant. We've already worked that out, so it's a bit pointless. I don't know why they're asking that question. So that's 15 complete.